again, thank you for the nice introduction. Hello everybody. Actually, all of you knows the technique of the parallel coordinates, which is well investigated yet, but the continuous parallel coordinates are not that well investigated, and therefore I present in my talk the features in the continuous parallel coordinates. So, I will give it first an introduction in the visualization approach of the continuous parallel coordinates, and then, I give also an introduction in the related continuous scatter plots, and yeah, let's do it. Here we have two-dimensional scalar fields, and one measures the pressure, the other measures the temperature of an arbitrary physical system, and let us now consider some domains of the system. The first domain is the spatial domain. It's the domain where the data are measured. It's this domain here. And the second domain is the domain of the measured data, the pressure and the temperature, and this is the data domain. And if we arrange the axes of the data domain parallel, then we get the so-called parallel coordinates domain. So, if we select now an element from the spatial domain, then we get also a representation within the data domain. And if we consider now the components of this representation within the parallel coordinates domain and connect them by line, then we get also a representation within the parallel coordinates domain. Now let's consider some of those representations within the parallel coordinates domain, which intersects each in a single point. Then we can see that we get also a relation between a point in the parallel coordinates domain and a line in the data domain. And this is a so-called point-line duality referring to Inselberg. And point-line duality actually means a point in data domain relates to a line in parallel coordinates domain and vice versa. So, if we select now a lot of those elements over our spatial domain, then we get over the data domain a discrete scatter plot. And over the parallel coordinates domain, we get the discrete parallel coordinates. This is actually known, or very well known. If we now increase our rasterization more and more until we will reach the limit, then we get over the data domain the continuous scatter plot, and over the parallel coordinates domain the continuous parallel coordinates. The continuous scatter plot has been introduced 3 years ago, 2008, by Bachtal and Weisskopf, and they defined actually a scalar density function between an n-dimensional spatial domain and a normally two-dimensional data domain. And this density function is based on a map function between both spatial domains. In my talk, I discuss only two-dimensional and three-dimensional spatial domains. So actually, then the color-coded density function is our continuous scatter plot. And later in 2009, Heinrich and Weisskopf defined the continuous parallel coordinates. And what they did was they defined that for a certain point in parallel coordinates domain, the density is given by integrating the density over the corresponding line in data domain. And then again, the color-coded density is our continuous parallel coordinates visualization. Of interest for my discussion actually is that in those continuous visualization approaches we can see some very salient features. For example, you can here see a feature in the continuous scatter plot, or here's a very strong one. Or in the continuous parallel coordinates you can see a feature here, and so on. And actually the question is, what are the causes of these features? And last year we introduced already the features of the continuous scatter plot, and this year I will subsequently explain now the causes of the features in the parallel coordinates domain for the continuous parallel coordinates. And for this, use my outline. At first, I will say some words to our previous work, the features in the continuous scatter plots. And then I introduce the features in the continuous parallel coordinates. I will show that these features are related to the features in the continuous scatter plot. And I will illustrate the results or our concepts, which sound, I hope, nice for you, nice applications. So, And then I close my talk with a summary and explain some impacts for the feature-based data analysis. Let us start with our previous work. Last year we introduced the features or the discontinuities in the continuous scatter plot, actually for two-dimensional and three-dimensional or spatial domains. And for example, here's a two-dimensional spatial domain and the related continuous scatter plot. And what we did is we defined a characteristic surface based actually only on the map function between both domains, as is this formula here. And then we showed that the boundary edges of this surface, which is also related to the boundary of the spatial domain, is related to feature curves in the continuous scatter plot where the density makes a jump, which we call edge curves, of course. And the zero crossings of this surface relates to features in the continuous scatter plots where the density is infinity. And we call those curves trend curves. The 3D case is a little bit different, and therefore we introduced a characteristical vector field, again, which depends only on the map function. And in this vector field we show that there are salient feature lines. And the feature line which has a cell behavior links actually to the track curves in the continuous scatter plot. And the feature line which has a center behavior, as well as the boundary edges again, links to edge curves in the continuous scatter plot. So we got finally this classification for the features in the continuous scatter plot. We see that there are edge curves or a track curve, and the point which is actually important is that we have only features which are based either on boundary effects or map function-based effects. And then the question occurs, are there actually counterparts of these features also in the parallel coordinates domain? And this is what I will discuss in the following. I discuss at first the boundary-based features and then the little bit more complicated map function-based features. So, at first, let us start with the boundary-based feature curves. We have here in the data domain very salient edge curve, and this edge curve can be locally described over its curvature by an oscillating circle, which is actually a disk of a line A, where A defines as the density in the data domain. And let us now consider a line in the data domain. Then the density of the corresponding point in parallel coordinates domain is given by 2 times A times mu, where mu is just the intersection between this line and this disk in data domain. And by moving now this line out of the disk, we can see that this mu decreases linearly, and this means that the density in parallel coordinates domain also decreases linearly. And then we get an edge curve from the data domain links actually to nothing in the parallel coordinates domain. This is what we call the smoothness effect. And this is our first result. So, let us switch now to the map function-based curves. Because they are a little more complicated, I will introduce at first a characteristical scalar field. It will combine the density of the parallel coordinates domain with the density of the data domain. And this facilitates actually the investigation of the counterparts in both domains. So let us do it. We have here a point in parallel coordinates domain, and this point is related to a certain line in the data domain, for which the slope depends only on this eta1 value here. And again, this line is related either to a 2D curve or to a curve in a 2D spatial domain, or to a surface in the 3D spatial domain. And if we consider now a point on this line, then it spans with its directional vector parallelogram, for which the area is given by this formula here. This one. So, and the point is, this area is constant for each point on this line. And this means that all area values for all those lines which have the same eta1 value spans actually this scalar field given by this formula here over the spatial domain. And this scalar field is very interesting because it has some nice properties. The first is the critical point of this scalar field is the integration of the gradient over the corresponding curve in the scalar field, or the surface in the scalar field, either in an arc-length parametrization or area preserving parametrization. And this is summarized by this formula here. And that, in order to investigate the counterparts between both domains, we need only to consider the parallel coordinates domain's density nearby the critical points in the scalar field. And this is what we will do next for 2D and the 3D spatial domains. Let us start with the 2D spatial domain. The 2D version of this scalar field has actually either center critical points or satellite critical points. And if we converge now our line in data domain, this one, against a feature point which has a center behavior in the scalar field, then we can see that the density in parallel coordinates domain is actually constant in a first order approximation. And at this feature point, the density shrinks to 0, makes a jump. And this means that a feature point which has a center behavior links actually to a point of an edge curve. If we converge now a line against a feature point which has a center behavior in the scalar field, then we can see that the density increases and is infinity at this feature point. And this means that a feature point which has a cell behavior in the scalar field links to a point of an attract curve. So, and now, if we collect all those feature points over the entire range of the eta 1 values, then we get the final feature correlation for the 2D case. We can see that an attract curve which has a center behavior links to an edge curve, and an attract curve which has a center behavior links to an attract curve in the parallel coordinates domain. And this behavior between the features relates also to the so-called curve duality, which is very well described in the literature. So let's switch to the 3D case now. Now our scalar field has again either center or satellite critical points, and if we converge another time our line against the feature point which has a center behavior, then the density increases or shrinks actually to 0. And this means that the feature point which has a center behavior disappears, and this is another proof of our smoothness effect. And if we converge finally against the feature point which has a center behavior, then we can see that the density at first increases, and starting from this feature point, the density decreases. And this means that the feature point which has a center behavior links on a point where the density is a local maximum, on a point on a ridge curve. And again, finally, we can collect all those feature points over the entire range of the eta 1 values, and get finally that an edge curve disappears in the parallel coordinates domain, and that an attract curve links to a ridge curve. It changed its behavior. So we get finally this classification for the features in the parallel coordinates domain, or where the continuous parallel coordinates. And two things are salient. The first, only attract curves from the data domain have a counterpart actually in the parallel coordinates domain. And the second, which follows from that, there are no boundary effects from the spatial domain visible in the parallel coordinates domain anymore. And I would like to illustrate these two nice effects now for some applications. At first, we discussed the 2D case. We have up some flow data of the German byte, and down are some synthetic data. In the middle is the continuous scatter plot, and then the continuous parallel coordinates follows. And I emphasize now the map function base features by some green structures and the gray-colored boundary based features, and by showing the equivalence now in the parallel coordinates domain, we can see that yes, there are no counterparts for the gray-colored boundary-based features. We can see it here, for example, or here is also no counterpart. But for the green-colored map function feature, there are very salient counterparts, the yellow lines. Okay, and this proves our 2D concept. So let's switch to the 3D case. Up there are some cycling simulation data visible. and down are again some synthetic data, and we show again one other time the green-colored map function-based features and the now white and gray-colored boundary-based features. And by showing another time the equivalences in the parallel coordinates domain, we can see at first the white-colored or gray-colored boundary-based features, for example here, have no counterparts. But please pay attention for these very weak structures here, for example. The green-colored map function-based features have very weak counterparts, but nevertheless they have counterparts. These are the mentioned ridge curves. And this proves also our 3D concept. So, to complete my talk, we introduced actually models for the 2D spatial domain and the 3D spatial domain for the continuous parallel coordinates. And I showed that there are relations between the features in the continuous scatter map and the features in the continuous parallel coordinate. And actually, the question is what is the benefit now for the feature-based data analysis? And as I said, in the parallel coordinates domain, the boundary effects are visible anymore. And boundary effects are not really information of the data themselves, because they are just an information where we stop to measure data. But what we would like to see are normally information of the data. And this information are coded in this map function. And therefore, in the parallel coordinates domain, only effects of the data are visible anymore. And therefore, one could claim that the continuous parallel coordinates are a little less confusing, especially for very inexperienced users. Nevertheless, there are still some challenges for the future which we have to solve. At first, as you see, noise influences the position as well as the number of features. And then the question occurs, which are the important really data-based features and which features are just caused by noise. And we are not able to distinguish this yet. And another challenge is, if you would back-project the features from the parallel coordinates domain onto the spatial domain, you would also get structure information. And then the question is, what does this structure information in the spatial domain actually mean? And this meaning is all not known yet. We hope to solve these challenges in the near future. But for this time, I conclude my discussion about the features in the continuous parallel coordinates, and say thank you for your attention.
You essentially work from the data domain over into the parallel coordinates domain, identifying features. Have you also thought of doing the inverse? You a little bit mentioned at the end, but others were thinking that, let's say you look at density, high density points in the parallel coordinates domain, which you would usually identify with some kind of correlation of the data. Have you thought of directly moving those features, or first identifying those features in the first place and then mapping them back into data and spatial domains?
Exactly. Yes. But as I said, this is really future work. We have to develop at first linking and crushing concepts to get the information, the data information, the structure information from the visualization back onto the spatial domain, for example, onto the data. And this is unfortunately not done yet, but this is a work in progress, and we work actually on that. And maybe in the next year I can present the results and can explain which features are mentioned by the feature structure and the visualization in the data. So it's work done, or work in progress.
Do you have time for another question? Have you thought of increasing dimensionality of the original domain, let's say going from a 3D spatial domain to a 4D space-time domain? And if so, do you have any idea how those structures will map back into those high-dimensional original domains?
Okay. No, not space-time, but what I actually would like to have is a 4-dimensional or 5-dimensional feature detection approach, but the problem is that those feature detection approach leads to integrating surfaces or subspaces and higher dimensional spaces, and we have now close solutions for this here. I would be very happy to have it, maybe also next year.